Hello everyone. I'm probably going to get started. I've got quite a lot to get through. So, yeah. Cool. So, I'm Tom, and I'm going to be talking about crushing the OSD variance problem. So, a little bit about me. I'm a Sysadmin. I work at the Rutherford Laboratory, which is part of the Science and Technologies Facilities Council. My main job is working with researchers and helping them store data. Yeah, and I started looking at Ceph in around 2015. I think the release of Firefly was the first one I looked at. And my main focus has been object storage for high-energy physics experiments, but we use it for a lot of stuff on site. So this is RAL. This is in Oxfordshire in the UK. The STFC runs sort of large experiments and facilities that other people can't afford to run or are too big for them to run. So we provide these to universities, businesses, and industries for them to use for research. I work in the scientific computing department, which is involved in facilitating those, providing compute and storage for those experiments, as well as international collaborations. So this is Echo. This is the largest Ceph cluster we run. It's been in production for, I think, 2 years now. And it's currently, it's just ticked over the 40 petabyte mark of raw capacity. And its primary, all the data pools are EC8+3, so that's 29 petabytes of usable storage. The main user by, amount of space used are the LHC experiments, so high energy physics experiments in CERN. But we have other users as well, and we've sort of been bringing more users onto Echo. I'm not really going to talk a great deal of detail about what Echo is, what the hardware is, and how we use it. I talked about that a lot last year in Beijing, and I'm going to link that talk at the end if people are interested. So who's using Echo? So we've got the existing high-energy physics experiments at CERN. We've started storing data for existing experiments that have been interested in using Echo or something like Echo. So that's Diamond, which is on site, and that's LIGO. And then we've got new experiments and communities that are interested in using something like Echo for their data storage, sort of a more object storage type model than the traditional scientific data storage. Since the last time I talked about Echo, a few things are kind of obviously different. The main one is it's a lot bigger. So that's the graph of the capacity in the last 15 months or something. And when I talked about it last, it was just over 10 petabytes. And it's now, it's tripled in size. I think we're a few OSDs below 5,000 OSDs currently, but we did reach that. And it's 180 storage nodes, and this is, and it is still growing. We have more hardware coming. We're sort of aiming for a steady state of around 6,000 OSDs for this cluster. Obviously we're not just making it bigger for fun, for our own amusement. We're storing more data, and currently there's 20 petabytes of scientific data in it, so that's 28 petabytes of raw capacity used on this cluster. So, what do I want to talk about? I've got two topics I kind of want to touch on. And the first one is the title of the talk. It's Managing OSD Utilization Variance at this sort of scale. I'm going to talk about what I actually mean by that, what works or what worked for Echo and what didn't work for Echo, and sort of explore how that went. And then with the second half of the talk, I'm going to be talking about what it's been like having that massive increase in the size of the cluster while continuing to run production work, and how Ceph, and particularly how the actual data placement worked at that scale, whether it worked as I wanted it to. So, it's a collection of words. What does it actually mean? What do I mean when I say this, and why do you guys care about it? Why do I care about it? So Crush it's sort of the heart of Ceph. it controls what placement groups end up on which OSDs and which data ends up in which placement groups. If you randomly distribute placement groups onto OSDs, you end up with a normal distribution of your OSD utilization or placement groups per OSD. So that's what a normal distribution looks like, or a Gaussian or a bell curve. You can call it a number of things. So yeah, it's a histogram. You've got your frequency up the side, your number of OSDs, and you've got your utilization along the bottom. I'm going to talk through this because I spend a lot of time talking about this, and I want to make sure we're all roughly on the same page. So on the left of your distribution, you've got your underfull OSDs. These are the ones that, in general, have less placement groups than the average OSD in the cluster. And if you can't figure out how to get more placement groups onto that OSD, you're never going to be able to use the space in it. It's always going to be less full than the rest of the population, and that's wasted space. And then on the other end, you've got your overfull ones. These are, as you would expect, the ones that have more placement groups than average. And as you put more data into your cluster, these ones are going to fill up first, and they're going to fill up fastest, and they're going to cause you problems first. And so if you can't move data off these and bring them back into the average, they're going to control how full you can make your cluster. And then, yeah, in the middle, you've got the OSDs that you wish all of your OSDs were like, and you ideally want your distribution, you want the center to be a nice big spike with very little spread. Okay, just a little bit of a reminder. I'm going to talk about standard deviation a lot. It's just a easy, well, it's a way of defining how much spread there is in your variation, or the variation of your population. And the variance is just the square of that. And yes, I will be using those terms basically interchangeably throughout this talk, so I apologize. So, what does it look like in reality? I've said it should approximate a normal distribution. Is that true? So, yeah, pretty much. So this is Echo last year sometime. There's 3,000 OSDs in the cluster at this point, and we have something that looks very much like a normal distribution. I think my favorite part about this is the incredible spread that Echo is demonstrating. So you've got OSDs that are over 80% full, and you've got OSDs that are under 20% full, which when you're thinking about like utilization and wasted space, that's just, it's not particularly good. It's, caused some problems. So how do you control this? Why do you end up with a spread of any width? Why do the widths differ? The main thing that makes that, in my opinion, the main thing that you care about is the number of placement groups per OSD. If you were to take an example, sort of a fairly absurd example, if your average number of placement groups per OSD was 2, and so Crush is pseudo-randomly distributing its placement groups onto OSDs, you're relatively likely to get OSDs, given enough OSDs, relatively likely to get OSDs with no placement groups on them. So your spread is all the way down to 0% utilization and is probably a similar amount over the top, because you're likely to get double the amount as well. To go to the other end of that example, if you have hundreds and hundreds of placement groups per OSD, you're still going to have outliers, you're still going to have a normal distribution of OSD utilization, but it's essentially impossible to get an OSD that has 0 placement groups. It's very, very unlikely. And similarly, you're very unlikely to get an OSD that has somehow got double the number of placement groups. So you bring that spread tighter together, and that improves your distribution. Having said that, and having thought about that, it doesn't necessarily, you can't use that, or at least we found we couldn't use that with Echo to improve our distribution. I think the way the maths works is you need to quadruple the amount of placement groups to halve your standard distribution of your deviation. For Echo, to get the standard deviation we were looking for, which was somewhere around 2, that was what we had calculated to be able to run the cluster as full as we needed to. We needed to increase the number of placement groups by somewhere somewhere, I think it was around 25 times, which was a pretty, we couldn't do that. We couldn't have that many placement groups and run the cluster. The OSDs were simply too overloaded. So we had to explore other ways of doing that. So I'm sure this is not news to anybody in here. If you fill up an OSD, any pool that has placement groups on that OSD is now full. You can't write any more data to it because you can't control which OSD or which placement group the data is going to end up in. And yeah, this leads to this statement. Looking at your general usage statistics on a large cluster, or on any cluster, but specifically if you've got a large cluster with a large variance in OSD utilization, the numbers can be incredibly misleading. So if you look at the example here, the cluster is just over half full in terms of raw used capacity. But if you look at the fullest OSDs, we're over 80%. And if you were to try and write another 8 petabytes or so into that cluster, you would run out of space very quickly. I'd say there's probably a space for another 1 or 2 petabytes before your fullest OSDs are approaching 100%. And so they're not particularly useful to statistics. They're not useful numbers to look at if you have a lot of variation in your OSD utilization. And because of this, and because we had a production cluster that we were throwing hardware into, and we were throwing it in because we needed more space. We had more users, we needed to get access to the space, and we needed to get access to it quickly. This was a problem. This was something that was making my life kind of interesting. So, how did you control the utilization? And so, when we were doing this last year, this was the tool we had. I'm sure, again, you guys are probably aware of this. This is not something I would recommend using now. With Luminance, we have much better tools that I'll start talking about, but this is what we had to use. And so as a quick recap, the OSDs all have reweight values. It's separate from the crush weight, and it can be between 1 and 0, and reducing the reweight value will reduce the number of placement groups. It's to go into the specifics of what's happening at the crush calculation, the OSDs are effectively competing to be in the placement groups. They're drawing straws, which is why the algorithm is called straw, or straw 2. And their straws are sort of functions of the PGID, the OSD ID, and a few other things. The reweight value just comes in at the end and is multiplied. The length of the straw is multiplied by the reweight value, which will shorten the straw and move placement groups off it. It's a fairly simple concept, and reweight by utilization uses this to reweight down the fullest OSDs to try and ensure your data becomes better balanced. So what does that look like on, what does that look like on Echo, on the scale of Echo? So you're about to watch what will be, I think, a month of Echo in, I don't know, maybe 30 seconds or something. And you're going to see we run, I think, about 7 large reweight by utilization runs throughout this to try and improve the spread. And then there's also a bunch of other stuff going on, which I will talk about. So it's pretty obvious when you run a reweight by utilization. It's a very simple thing. It's pulling the top off the distribution and moving those, the end off. It's moving those full OSDs back into the mean. There's also a lot of other stuff going on. You'll see like the mean is sort of bouncing up and down. There's data going in, there's data coming out. The cluster's got a lot of stuff going on. We're doing placement group increases at this point, which is shuffling data around internally. We're adding hardware. This is just sort of small additions of storage nodes. So there's a lot going on. And if you've been keeping an eye on the standard deviation on the top left, we started at about 11, I think, and I think this clip ends there at about 8. So we have managed to reduce the standard deviation. We've managed to improve the spread of Echo through this month. However, as I said, it was a busy month for Echo. As I said, we ran 7 reweights, but large reweight by utilization runs that would sort of 2 to 3 days of backfilling for each one. This was sort of like effectively moving petabytes of data around the cluster over the course of a month to try and improve the distribution. And it was improving the distribution, but not at the sort of the rate we needed. And I think one of the things that's kind of noticeable from this clip is anything that isn't reweight by utilization, any cluster operation that isn't us explicitly trying to move data off full OSDs and onto other OSDs is increasing our utilization spread again. As soon as something else happens on the cluster, it's all sort of just like, squishing back out, and your OSDs, your fullest OSDs are becoming more full fairly rapidly. This makes it not necessarily, or this made it not work very well for us. Echo was always going to have a lot of churn, just the model. We're always adding hardware. We're always sort of bringing new experiments online. There's always going to be data shuffling around. And if reweight by utilization couldn't allow us to sort of do all the operations we needed to and keep the utilization in check, it wasn't really going to work for us. So there are a couple of reasons why I think it wasn't working for us. As I said, sort of the general churn was an issue. You can't add weight easily. If you have a very static cluster, you can add weight because you can weight everything down and you can run reweight by utilization enough that the average is weighted down and the underutilized stuff is then weighted up by still being at full weight. Again, that wasn't really going to work on Echo. We weren't finding the cluster was staying static for long enough that reweights were actually able to have that kind of effect. And then finally, the last point is the issue, I think, in particular with Echo for using reweight by utilization is it's sort of a continuous thing. It's like you instinctively say, well, if I weight something down by a few percent, I expect a few percent of data to move off it. At this point in Echo's existence, it had very large placement groups. So I think an individual placement group with around 5% of any particular OSD's total utilization. That was the big data placement groups. And so each OSD would only have a handful of those placement groups. And so if you're trying to move these off, you don't know the specifics of the individual calculations that determined how those placement groups ended up on those OSDs. You don't know the length of the straws. You don't know how much you have to reduce the length of the straw for another OSD to then take that OSD's place. So there's a lot of randomness in there that makes it inherently quite hard to manage a cluster if you've got large placement groups using reweight by utilization. So this was an interesting time for us. We'd been rolling with it for a while, seeing if we could get it to work, and it was becoming more and more clear that it was really not going to work for us. When we had sort of come up with Echo and got some money to buy hardware, we had got some money to buy an amount of hardware to provide for the scientists. An amount of storage. And we had based that on the assumption that we could run a cluster with an average utilization of 85%. It seemed fairly achievable. It may have been ambitious, but it was something that we thought would be achievable. However, in practice, that was not what we were managing. Yes, that's my trying to explain what would happen if you tried to run that distribution up at 85%. If you try and move the average up to 85%, it's not going to be a fun cluster to try and run at that point. And so this was a little bit concerning. There was much head scratching and, well, I don't know. But luckily, the Ceph developers had been thinking about this. And UpMap came along. So just very quickly, what's UpMap? UpMap is it's a different part of the crush, or it's a new part of the crush calculation that happens after you still do the crush calculation. You end up with a set of OSDs for a placement group. You then check in the UpMap, which is basically a hard override, which says, if this OSD is present in this placement group, replace it with another OSD. And this is really cool. Having the ability to actually forcibly move placement groups from somewhere to another explicit location is not something we've ever been able to do in Ceph before, and from sort of like a year of managing a large Ceph cluster, it was one of the pain points of if you got placement groups moving in directions you didn't want them to move, especially if you're thinking about full OSDs, you can reweight stuff down, but it won't necessarily move that placement group that is moving. It might move other placement groups, but you're still stuck with placement groups moving in the wrong direction unless you get lucky. So having this tool is really cool for that. The balancer uses UpMaps to move placement groups around to balance your cluster, as the name would suggest. It has straight from the beginning, it has the potential to be a lot more efficient than something like Reweight by utilization, purely because it can, as well as moving placement groups off full OSDs, it can move them onto empty OSDs or underutilized OSDs. So you can reduce your spread from both ends, which is useful. It also, I'm not going to talk about it, but it's a lot more cleverer than I've just described. It's a really cool bit of kit, and it balances the cluster really well. Dan gave a really good talk at Ceph Day Berlin. I will link those slides at the end. A lot of the work I'm going to describe is based on what Dan suggested would be a good way to do it, and so I will link those at the end, and I'd encourage anyone to check them out if they're interested. So, started off by having a bit of a test on one of our small clusters, and yeah, it did exactly what it was meant to do. It was a very convincing test. We went from sort of a fairly standard spread to a very it's no longer really a normal distribution at that point. It's just all OSDs being within 2% of utilization of each other, which is exactly what you want when you're running a Ceph cluster. You really don't want to be thinking about distributions and standard deviations. You just want data, all of your disks to be the same fullness. So, after this, it was a very easy decision to switch Echo over to using UpMap Balancer, and that's what we did. So, I think this clip is going to be about 4 days of balancing in total. So we start, the standard deviation is somewhere around 8, and then it all just sort of goes zoop, and your cluster is a lot better balanced. So that's a standard deviation of 2, which is pretty good. That was kind of the number we were aiming for, and this was very awesome. However, it wasn't perfect. It wasn't that perfect distribution that we saw on the dev cluster, and I did a bit of poking, and it turns out we had run into an issue that affected large numbers of OSDs, which had already been found by Dan, and had already been fixed, which was cool, and we just waited for the backport. And then turned it on again, and saw what happened. So again, this is, I think, another 48 hours of balancing. And yeah, it worked really well, actually. I was pretty impressed with it. So this was kind of, I'd spent probably the best part of a year looking at all these histograms and being like, oh no, how is this ever going to work? And then I come in on Monday morning and there's 2,000 OSDs in like 1 percentage point bin, and it's like that'll do it. So yeah, it worked really well. Our total utilization spread had dropped to 5%. So compared to the sort of 40% we were managing at a push earlier, this was incredible. And the thing you really care about is the distance between the average of the distribution and the fullest OSD, because that's the thing that controls how far up you can push the average, the average cluster utilization, the average OSD utilization before your cluster is full. And so if you imagine trying to run both of those clusters at 85% full, one is completely possible, the other one is definitely not possible. So it was that sort of difference, that sort of extra headroom you get that is really, really useful. Sort of a rough eyeballing the new distribution. we had approximately 6 petabytes of extra space to play with now. We could comfortably run the cluster at above 80%, 85%. Yeah, we can run at 80% without even changing the default full ratios, which was really cool. And once we get more comfortable, we can push it higher and higher, and once we're happy that the UpMap balancer is working as expected. Yeah, I think the thing that I found really interesting about this was how efficiently it did it. So as I said, I'd spent months trying to balance the cluster using Reweight by utilization, moving, yes, actual petabytes of placement groups around and then having them move back or move in the wrong direction. And it was sort of it was very much a guessing game. This took a week of combined backfilling to balance 28 petabytes of data, which was, yeah, pretty amazing. And the cluster was in production throughout this whole thing. This is kind of, this is kind of hard to look at, I'm sorry. But the red is the rebalancing traffic. So we were sort of doing anywhere between, well, average of sort of 30 up to 50 at the end. But we were doing sort of 20 to 30 gigabytes of read traffic, production read traffic throughout the whole thing with no issues. And that's sort of fairly standard for Echo and for a Ceph cluster like this. So yeah, UpMap was really cool for us. So now with the rest of the time, I want to talk about what it's been like adding this many OSDs to a cluster. I'm not actually going to talk about sort of the administrative sort of thing, like what deployment tools we used or anything like that. I want to talk about how Crush handled it, how once you've got those OSDs in, how the backfilling is handled, how the data placement is onto the new OSDs is handled. So, as sort of I guess to start it off, it went really well. It was, yeah, surprisingly pain-free, tripling the size of this cluster in a year. However, I think with all of these things, there are a few things you don't expect to happen, and one particular one I found quite interesting, mainly because it was such a headache when it happened, and then it had such a sane explanation when I figured out what was actually happening. So let's look at what adding OSDs to a cluster looks like. So this is towards the beginning of last year. Echo's 2,000 OSDs at this point, so this is right at the beginning of what we started doing. And I think throughout this clip, it's about a month, or just under a month, and we had 700 OSDs. And the OSDs we're adding are slightly bigger in terms of space, but they're normalized, so they're all the same height. So yeah, so this is adding sort of like batches of OSDs as we're sort of feeling out how the deployment process actually works. All of the new OSDs are coming in at half weight. We haven't been able to exhaustively test the hardware at scale. So putting them in at half weight means they've not got as many OSDs. We can check the memory usage, check the CPU, make sure it's all okay, and then once we're happy with it, we can weight everything up to 100%, and the distribution will sort of go. I had a lot of fun making these animations. It was an enjoyable couple of weeks. But yeah, and so that's what it looks like. So you can see, yeah, we've gone from the cluster at the, oh wait, can I do that? Yeah. So the distribution at the beginning was sort of around 70% full, and then at the end, I can't skip to the end, I'm sorry. But the distribution at the end was about, well, substantially less full, 60-something% full. So what was that? So that was adding 50% of extra capacity to a production cluster in under a month. It was a 12 petabyte cluster at the beginning of that, and we added 6 petabytes of OSDs to it. This cluster was fairly full. It was 70-something% full when we started the operation. So there's 8 petabytes, or nearly 8 petabytes of data in the cluster that has to be shuffled around. A third of that data has to move. So yeah, this was all done while the cluster was serving production traffic. This was not noticed by anyone. We didn't have any complaints about this. It was all handled properly by Ceph in the background, which was really good. There was, however, some unexpected placement group movement. So where that arrow is pointing, I'm not sure if anybody noticed, the bulk of the existing OSDs sort of are moving down. You get the occasional one that kind of tries to make a break for it, decides it wants to be more full, which was, yeah, fairly problematic for a full cluster when we started adding hardware and you've got OSDs that are 80-something% full, suddenly trying to get more full. It's a little bit confusing. And so, yeah, the title was my initial reaction when I was trying to figure this one out. So I did a little bit of working out what was actually happening. And it turned out, yeah, most of the placement groups were doing exactly what I expected them to do. Or most of the data movement was in the direction I expected it to be in. We had placement groups moving off existing OSDs or out of existing crush buckets and into the newly added crush buckets. However, if you look at the script output, we had some placement groups moving onto existing hardware, onto existing storage nodes. So, yeah, which isn't really what I expected. The only place they can have come from is other existing storage nodes, and that kind of violated what I thought Straw 2 should be doing. Yeah, the assumption is always that it will do optimal data movement. You weight up a bucket, data will move into that bucket, it will not move between existing buckets. You're not changing anything in the new buckets. There's no reason for placement groups to move between those OSDs. So it turns out I actually hadn't thought about it hard enough. And it's sort of, I was thinking about it too simplistically. And yeah, you kind of need to step back a little bit and think about what's actually going on here. So when a placement group has a set of OSDs, and that set of OSDs must obey the failure domain. I'm sure everybody is happy with that. That's not particularly revolutionary. And so Crush has to deal with that. Crush has to not return you sets of OSDs that have OSDs on the same host, assuming your failure domain is on the host. So Crush does this. It does the calculations one by one to produce each OSD for the set. And so if it produces an OSD, and then it produces the next OSD, and that OSD collides with the first OSD, it has to redo the calculation, and it's just got a value that it increments, which changes the output and produces a new OSD, or a new Crush bucket. I've kind of generalized on this slide. And assuming that doesn't collide, that's then in the set. So that's your set. And this is great. This is a very elegant way to solve the problem. It's repeatable. Everybody knows the Crush rule set. Everybody knows how to do the Crush calculation. Everybody can do this calculation, and everybody can get the same result every time. However, it leads to an interesting edge case that is what I was seeing here. So when you've got this collision and the second OSD has to choose a new value, what happens when that first OSD, the one that caused the collision originally, leaves the set? So say you add a whole bunch of new hardware, you get placement groups moving off existing OSDs. If one of those existing OSDs in a set was causing the result to be changed further down the set due to a collision, the only deterministic thing to do is to revert that or redo that calculation which now doesn't contain the collision. So what that means is, so if you look at the example here, this is a placement group that I was looking at the time. So shard 0, the first item, the acting set is what it was, and then the up is what it is now. I've added new hardware. So we've gone from 1811 to 3001. So we've got this placement group has moved onto one of my new OSDs. And that's fine. That's very, very understandable. What you've also got is OSD 111 that has now been replaced by another OSD that is on an existing host. They're both on existing hosts. They've seemingly just switched randomly. Now that I've sort of talked through it, it might be apparent that because OSD 1811 and 1833 share a host, 1833 actually was the original answer for that shard 4 in the set. So Crush originally, when it ran, said, oh, I want 1833 to be in that position, but that collided with 1811, and so Crush had to increment the retry value, and produce a new result, which was 111. And so what that means is, yeah, and so the set contained 111, but once the OSD that was causing the collision was removed, you then end up with a movement happening between existing hosts. So yeah, this was a bit of a pain point. I should add at this point, the amount at which you will see this happening entirely depends on your cluster and the size of your placement groups. It's the relationship between the size of your OSDs and how many failure domains you have. So you're more likely to see this with big placement groups with few failure domains. If you're more likely to see collisions, you will get more of these collision replacements happening in each of your placement groups. So, yeah, this is, once you understand what's going on, it's not that scary. You can reweight the OSDs down. Placement groups will move off them. If you've got sort of 20% objects misplaced and a few thousand placement groups in backfill weight, it can take a little time for these things to start, but in general, it kind of does just manage itself. However, you do keep getting woken up in the middle of the night by OSDs getting fuller and fuller, which can be annoying. The main reason why I found this, or I think this can be quite troublesome, is there's no visibility of it. OSDs don't keep track of how much data is moving onto them, so there's no warning that an OSD is trying to fill itself up. It will just do it, and then it will hit one of the ratios and then trigger a health warn or a health error. This is a little bit frustrating. So I wrote a couple of very hacky scripts to help me with this. It's tools to help me visualize placement group movement. So the first one is basically Ceph OSD DF, but with 2 extra columns, which tell you if they have placement groups moving on or off of them. And you can run it against an individual OSD, and it will actually give you more information about which placement groups and what states they're in and when they started backfilling and stuff like that. And then the other tool is just a simple thing that essentially looks at all placement groups that an OSD is in the upset of, so one it's meant to be in, looks at the sizes of those placement groups and calculates what that will mean for the final utilization of that OSD. Having a couple of tools like this, and then sort of building loops around them, meant you can kind of iterate over your fullest OSDs when you've got weird placement group movement, make sure you're moving placement groups off, and make sure things aren't going to end up full. I will link these at the end if anybody is interested. They are very hacky. They were written for a purpose very quickly, and they should work, maybe. So yeah, right, so finally, one of the other things Dan mentioned in his slides was adding OSDs using PDFmap. So very briefly, you add in all your OSDs, you upmap all the placement groups off them, and then you let the upmap balancer remove those upmaps and move placement groups back onto them. It gives you much more control over the operation. It sort of is, rather than making a big bulk reweight where you end up with 10% objects misplaced, and that's like a week of backfilling, the upmap balancer can make sure there's always like a fraction of objects misplaced, which means that you're not having placement groups waiting for backfill. This means that if you then hit OSD failures or anything else which you expect with a cluster this size, there's no large backfill queue that the degraded placement groups get stuck in. Everything can start straight away, and you can return to a non-degraded cluster a lot quicker. So yeah. So in conclusion, the OSD additions this year went really well. It was a little bit. We hoped it would work well, and it was the thing that was sort of sold Ceph for us, is the whole idea of these data placement algorithms that didn't have they only had optimal data movement when you're expanding clusters. It was always the model we were going to have with Echo is always going to be small new generations of hardware every year, and so we need something that can cope with that, and we can add hardware in and not have to completely changed our data distribution over our cluster. OSD utilization variance has been a big part of my year. It's been something I've been thinking a lot about. I've learned a lot of interesting things. I've had to go back and sort of rethink about how Ceph actually works. Things I thought I understood, I definitely didn't understand, which has been fun. And the UpMap balancer has kind of solved all of those problems. So I maybe could have just waited 9 months and waited for UpMap balancer to come out. But yeah, the UpMap balancer is fairly amazing. It works as expected. We have petabytes of extra usable space on this cluster. And yeah, it's going well so far. So yeah, thank you very much. Thank you for your time. Those are the links I talked about. And yeah, that's pretty much it from me. Thank you. I'm not sure if I've got time for questions. Oh, there is a question.
Did you say anything about throughput and latency?
Pardon?
Did you say anything about throughput and latency? I think when the distribution goes like this,
Yeah.
the latency will probably suffer. What did you see?
So yeah, we have the luxury with Echo of not our cluster is not the cluster use case is not latency sensitive. This is all high throughput object storage for high energy physics and other stuff. So we don't really track that sort of stuff. We haven't seen anything significant. I'm prepared to believe there may have been a change, but not anything noticeable for us. Cool. Sorry.
Is there any reason to have the rewrite script you are using with the new UpMap balancer?
So the question was, is there any reason to use reweight by utilization?
The script.
The script I wrote. No, well, not necessarily. With UpMap balancer, you don't. It controls the OSD distribution well enough that I don't think we're going to be running into those problems. You will always have problems, and as I said, the way Crush works, you will always have the edge cases where placement groups move in unexpected directions. You can use UpMap to, rather than having to reweight stuff down, you can now use UpMap to move placement groups if they're moving in the wrong direction. If it's critical, if it's sort of effectively if you're in an emergency situation, you still need to be able to identify those placement groups. And so the stuff I put up there was more about being able to identify placement group movement and what that meant for OSD utilization, which will always be a problem. I mean, UpMap has made our cluster, we can run it a lot fuller, but we will run it a lot fuller, and we will run into the same problems.
Hi, yeah, I just wanted to point out that these really awesome UpMap improvements over the last few months have come from the engineers at ZTE. They put in like a lot of really key fixes, and it's making it, like you said, like, totally awesome. Yeah. Yes,
yeah, thank you very much. Yeah, it's been absolutely fantastic, and yeah, I've got some help today or yesterday from Zai, which was really useful. So, cool. All right then, thanks very much, guys.